Or, not quiz, no points taken off, only fun learning. So I'm going on a vacation. I can't pack all my luggage in my car because I don't know, I'm taking too much stuff with me. So where should I put the luggage for the lowest drag? I can either put it on the roof rack on top of the car, or I can get one of those little bumper or hitch racks and put it on the hitch rack. Where should I put it to get the best fuel mileage? Of course, the real answer is just don't take so much stuff on your vacation. But you know, what's interesting is on the hitch behind the car, you're essentially putting your luggage in the wake. And it's already in the wake. The added drag is minimal. I'm sure there's probably some additional effect, but it's tiny. Whereas putting it on top of the car, not only do you make the streamlines get closer together at the points of separation, but you also make the area of the wake bigger. You increase the size of the wake, and the force of drag is equal to the pressure related to the difference in pressure in the wake times the area of the wake. So you are right, put it on the hitch behind the car. Thank you, good job. Okay, three questions, Patrick. Which equation do you use to measure the head loss in a pipe system? So you're going to design a pipe system and you've got to use some equation, and there's a control volume energy equation, there's a Bernoulli equation, and maybe they're actually the same equation. So which one do you vote for? Control volume, Bernoulli, or they're the same? And by the way, on this one, if you mess up, you're in really good company, really good company. This is probably more than a decade ago, but I was looking at the FE exam, and the review booklet for the FE exam had it wrong. So let's see. Let's find out why it's number one. So there's equation, the control volume equation, and it's a mess. It's got, what is it, 9 terms, too many terms for one equation. It includes things like HP, which is the head added by a pump and the head taken out by a turbine. And it does have head loss tucked away there. Then there's the Bernoulli equation, and goodness, if you look at those terms, it's like, what's the difference? They got the same terms in it. So you could justifiably ask, like, why is Monroe like drilling this one? Why does this one matter? Because they are so similar, except that there's some really big differences. So they are not the same equation. So let's talk about this. The assumptions that are needed in order to make it possible to use the Bernoulli equation are that it has to be along a streamline, it has to be frictionless, no lost mechanical energy, it has to be a constant density fluid, and it has to be steady. And the one of those that you really miss on a pipeline is it's not frictionless. Matter of fact, the thing that you were trying to calculate was head loss in the pipeline, which is like how much friction was there. And so the Bernoulli equation says, well, in order to use me, you can't have any friction. So Bernoulli equations don't work in long pipelines. There are places where we can use them inside a pipeline, and I'll try to make that clear before we're done with this. And here we go. Okay, so now we have 2 places where flow is going to go through a change in geometry. In one case, it's a smooth flow contraction, and in the other case, it's an expansion where the pipe gets bigger. And I've asked 2 questions: which flow loses mechanical energy to heat, Or alternately, that's the same as asking, where can you apply the Bernoulli equation to track what's happening as you go through this change in geometry? So what do you think? Which of these two, and you can in one of them, which of these two can you apply the Bernoulli equation and it's completely legit? And you know what? It takes a little bit of time to get the poll out there. I'm tempted to just do this by raising hands so we can do it faster. So who wants to vote for number one? Don't be shy. I see one. And Victor, you've had your hand up for a while, so I'm not sure if this is a new hand or an old hand. Okay, so there's 1, 2, 3, 4. I've got, oh, and there's, okay, you can vote. Go for voting in the poll.
I think I've got it figured out now, so we can, the polls are good to go.
Excellent. And just take a second and then let's pull it in. All right. Okay, once again, if we were doing it by consensus, we got the wrong answer. And hey, you know what? I apologize. I just realized that the two questions I asked were contradictory. So the poll is a wash and Monroe fails this part of the course, okay? We'll have to do it like that. Monroe failed. And so I can't make any sense out of what you said because I don't know which question you were answering. So I'll just proceed with the answer. That's so funny. I worked hard over the last couple of days to revise these notes to make them clearer, and I clearly failed in that one. So which flow loses mechanical energy to heat? That is the flow expansion. Where can you apply the Bernoulli equation? That is the smooth flow contraction. And when you took fluids, I bet you learned that you lose energy when you go through a contraction in a pipe, which is true. But if you go through a gradual contraction, you don't. And it's kind of fun to understand why do you lose energy in a sudden contraction? And hopefully by the time we're done with this, you'll get that. So smooth flow contraction, we can apply the Bernoulli equation. So in that case, mechanical energy is conserved and it's completely legitimate to use the Bernoulli equation along a streamline. So we can take a point there and a point there. And what that tells us is that as we go from 1 to 2, V2 is higher, elevation is the same, so that must mean that P2 is lower. So the pressure drops as we go from point 1 to point 2. Energy was conserved, we just converted some potential or pressure energy into kinetic energy. In a flow expansion, there's some weird stuff that happens. And the weird stuff is that after the flow exits that first part, it generates all kinds of turbulence because it has high velocity and it's trying to flow into a low velocity zone. And that high velocity means its flow has momentum, it's got inertia, and it doesn't know what to do with it. Okay, it's not actually human thinking about this, but it's like, I need to slow down. What am I going to do with all this inertia? And it starts like turning off to the side and creating eddies and spinning up and creating turbulence. And then that turbulence ends up dissipating a bunch of the energy. So you end up getting something that looks like this. So you have this very chaotic zone. Sorry, it should have been blue because there was blue water in here, but I didn't have I used red dye number 40 to get this image, so it's red. So that you have this turbulence, and that turbulence is dissipating mechanical energy and turning it, kinetic energy, and turning it into heat. And that means that we cannot use that equation. Bernoulli equation does not apply for that second case. So some mechanical energy is converted to heat. Okay. Let's try this one. We'd like to understand how much water comes out of the hole in the side of a bucket or in the bottom of a bucket. So we're going to figure this out using an equation that we're going to derive, that's the orifice equation, but we're going to use Bernoulli because in here, we notice that if there's a contraction of the flow, we can use the Bernoulli to track it. Oh, I want to give this conclusion. When there is a flow contraction, Bernoulli equation can be applied into that flow contraction. Whenever there is a flow expansion, Bernoulli equation cannot be applied. Okay, so if the flow is speeding up, energy, mechanical energy is conserved. If the flow is slowing down, mechanical energy is not going to be conserved. So here we have flow speeding up as it's coming out the side of this tank. And so, and we're going to have a flow contraction. And so we can use the Bernoulli equation between some point on the surface of the tank and some point in the middle of the jet that's coming out. Technically, these have to be on the same streamline, but you can imagine there's a streamline that starts at the surface of the tank and ends up going through this jet. So we're going to use the Bernoulli equation. The Bernoulli equation means that there's no mechanical energy loss. Nothing is being converted to heat. So let's look at this. The pressure on the surface of the tank is 0, so or it's atmospheric pressure. We can use that gauge pressure as our datum, atmospheric pressure as our datum. So P1 is 0. The surface of the tank is barely moving, so V1 is 0. P2 is also atmospheric pressure, very close. And that means that we're just left with, we don't know what the velocity is at V2, but look, we can get it from, if we set Z2 equals 0, that means that V2 is related to that delta H. And so there's a beautiful equation. V is equal to the square root of 2gh, which you probably saw that equation way back in physics sometime in high school. And that's if you drop an object, that's how fast it goes. So same thing applies to water coming out of the hole in the side of a tank, which is kind of cool. It didn't get there in the same path as dropping it, but it ends up with the same amount of energy and the same velocity. And if we zoom in on that orifice, this is what's happening. So I'm now following a streamline that is coming down along the side of the tank and then trying to take the corner and go out through the hole. And just like before, it can't do a 90-degree bend. It has to bend slowly. And the result is that we end up with the jet having a smaller diameter than the hole from which it came. Was that cool? The jet is smaller than the hole. I don't know if you saw that coming, but it's kind of cool. And it's why orifices work the way they work. So we call that contraction, from the fact that the streamlines had to bend, a vena contracta. And what we see is that the area of the vena contracta is less than the area of the orifice, and that the ratio is what I'm calling pi VC. So I use the capital letter pi to mean that I made a dimensionless ratio of two things. So a pi is always dimensionless. So this is my dimensionless ratio of these two areas, and it has a value about 0.6 for an orifice. So we have that equation, and we have the continuity equation that Q is equal to V times A, and we can add those two into the V equals the square root of 2GH, and we can get a nice equation for an orifice that the flow rate is equal to this vena contracta coefficient, about 0.6 times the area of the orifice. That gives us the actual area of the vena contracta times the square root of 2GH, and we're done. And I would say you should either, one of two things, you should either know like how you obtain that equation, because it's pretty straightforward, or you should just know it. It's a simple equation that describes how fast water is going to leak out of that bucket that you drilled a hole in the bottom. This equation would most easily apply to an orifice that's in a horizontal plane with the tank above it, so that the depth of submergence is constant over the entire orifice. If it's in the vertical plane, then for depth of submergence larger than the diameter of the orifice, that equation works too. So if the orifice is well submerged by more than like 1 diameter, then this equation works reasonably well. And if you want to be fussy about what happens if the orifice is only partially submerged, then there's a lovely link there for an equation. You have to integrate over the area of the actual orifice opening where water is flowing to get the flow rate. And I feel like, yeah, we can go one step further. We just have a little bit of time. So we've talked about drag. We've talked about the hemisphere cupped into the wind as being the awful system with lots of drag. And you're like, why are we talking about hemispheres going through air? This was supposed to be a course about drinking water treatment, and the fluid of interest is water, not air. So point well taken. Happily in fluids, we don't care. It's a fluid, and the physics is the same almost, except that water is not very compressible and air is quite compressible. But the other transition that we're going to make is that, oh, there's these cool similarities between the case of air flowing around an object and the case of water flowing inside a pipe. Yes, they're different, but a lot of the same physics shows up in both cases. So we talked a little bit about drag, about external flows. We didn't talk at all about shear on a solid surface, but indeed that's the skin drag, or the drag that you feel on a flat plate. That's the shear. That's important when you have a streamlined object. And the cool thing is that there's these nice analogy to what's happening inside pipes. So if we go to pipes, we have major losses, which we talk about as friction, and that's the same as shear, because it's also shear on a solid surface and it's shear on the pipe walls. So major loss is about shear on the pipe walls. Minor loss, and by the way, I think that calling them major and minor losses did none of us any good, because major losses can be minor and minor losses can be major, and those words don't actually help us understand what we're talking about. If you want to like correct it in your own mind, whenever we say major losses, you should be thinking about shear, and whenever we talk about minor losses, we should be thinking about the fact that there was a flow expansion inside the pipe, and we're talking about like a pressure drag. The total head loss is the sum of major losses and minor losses. And to be clear, head loss is just a measure